So, hello everybody. Has anybody tried TypeScript since last week who hasn't used it before?
Neither has.
Very good. At first, it is a lot of pain because most of you are unlikely to be used to the idea of creating types for your data. But as you use it more and more, it becomes second nature, and it really saves our butts a whole lot. We will start today with a recap of what we looked at last week. Last week we started by looking at some type errors. What are type errors? When the program is expecting a value to be of different type than it actually is, when we look for different properties, different behaviors than what we actually provide. Usually type errors happen across API boundaries. We know that splitting our program into multiple modules is a useful approach. Modules have APIs. The rest of the program uses a module only through its API. And so these APIs are often referred to as API boundaries. And that's where type errors are the easiest to happen, because often it's different programmers or one programmer, but at very different times. So type errors get in the way a whole lot. Programming languages are often distinguished on how they enforce types, because most programming languages have some kind of type enforcement. Dynamic typing languages, they enforce types at runtime. They check that values are of supported types. Now, some languages are very strict about it, and some languages are very lenient. JavaScript will allow you to add a number and a string, but other programming languages could easily throw an exception when you try to do that. To find if you have any type errors in there, at least those that the type system can find, you need to run the program, and then you check that it behaves. You have to do a lot to see if there's any type errors. Static typing languages, they make you tell the program, tell the computer what types you expect where, and then before you even run the program, the computer can check a lot of that. Languages like Java, C, C++, Go, Rust, and TypeScript, they are static typing languages. Now, they may also do some runtime checking, and that's part of it, because no static typing system that is actually useful can catch all type errors. TypeScript, the language, it is a programming language that is basically JavaScript with type annotations and some very useful tools. What are type annotations? We can put a type information on a variable. Here we have a constant message or a variable max, and we say they are a string or a number, and then we can assign values to them. And if we try to assign the wrong value, the compiler will tell us. In fact, the editor will tell us. If I open this right here and try to assign into message the value 0, then it will complain that number is not assignable to string, and it's absolutely a valid complaint. If we don't include this type information, TypeScript is happy to infer it for us. If we define a variable and put a string in it, TypeScript will assume that we always want to have a string in that variable. So that variable will then be typed as string. And in my atom, as I hover over MSG2, it tells me, if you focus, it's tiny, it tells me that MSG2 is seen as being of type string. I didn't have to say that. If I do make a variable where I want different types of values, and I want initially to put a string in there, I would have to say that it is, for example, string or number, and then I would be allowed to put a number in there later. MSG2 is 0, that's absolutely okay. But if I let TypeScript infer, it makes the wrong assumption here, but usually it's the right assumption anyway. Right. When we have functions, we can give types to their parameters, and we can give type to the return value. Void is a special type that says the function does not return anything. And then TypeScript will check all invocations for us. The basic types are Boolean, number, string. Then there's null and undefined, which TypeScript is forced to distinguish because JavaScript does. Then TypeScript has a few types unknown to JavaScript. Void is basically null or undefined. Any turns off type checking. We do not use any if we can avoid it. In fact, we can avoid it. So we just don't use any. Unknown is the type of a value that we don't know the type, and we can do various things with that. We will see that later. And never is a special type that we don't use, but the compiler can find that some value is impossible, and then it will say it's of type never. We can type our arrays. We just use some kind of type and put square brackets after it. We can type tuples, which are arrays of a static size. We can type objects, and we do that with something called interfaces. So if I open that, you will remember that we had an interface for a droid, and we can specify that name and color are required, or we could make color optional, and so on. We can have read-only properties that are only assignable at the start. So read-only name. Then we cannot, if I have droid1, I cannot do droid1 name is new. The name is read-only here. I can't change it. It's just like const. Interfaces can extend one another, and to see whether we can put one interface where another is expected, TypeScript uses something called duck typing. So if an interface fits the definition of another, the values that fulfill that interface can go where the other interface is allowed. Functions, like I already said, we type the parameters, we type return values, we can have required or optional parameters. We can give default values to parameters, which can also infer their type. And we can have REST parameters that have to be typed as arrays because they are always an array. Right. We are now moving past what we did last week. So I have an exercise for you. That's for after the lecture. We did a bunch of type error examples last week. We have 5 files in there that are examples of type errors. I will open the first one, and what we have here is we have a variable that we expect a number there, but actually we get a string, for example, because we get it as an input from the user. And then when we try to run this, we have 31 as the output of this, where we actually expected 4, because that's what 3 plus 1 is. And I want you to take these examples, take these erroneous programs, and turn them into TypeScript and see how you can make TypeScript find the issue for you. I will do it with the first one. I will rename this file from .js to .ts, which is the file name extension for TypeScript. Now it is one add number string ts. And now it's telling me that A is implicitly of any type. What do I want in A? I want a number there. And then it's telling me input number is of type string, and I can't put it where I expect a number. And I have found the problem. TypeScript has found the problem for me. And if I now change input number to number here, then it runs and it returns 4, and this is the correct behavior. So here I have taken an erroneous JavaScript program that wasn't complaining about anything at all, and I turned it into TypeScript. I had to add a type annotation, and then it found a problem for me. And I want you to do this with the rest of those files. So first step is rename it to something .ts. Second is check if TypeScript compiler already sees some kind of problem, because it did immediately, but it wasn't the right problem. It was telling me A doesn't have a type, which was correct. I'll open it again. Yes, this A didn't have a type. then you should fix the file so that TypeScript stops complaining, and you should, in that process, also fix the problem that the file was created to demonstrate. We would like you to do this and show us your code in the drop-ins. The drop-ins are usually very easy, so we have plenty of time there to check your work. There are 2 hints. In this example, you will want to create an interface for this object that's called somebody. And in this example, this is a web page. You will need to take the JavaScript, split it into a separate file, and then compile that. And then you can run the TypeScript, compile this JavaScript. And we'll see how to do that easily in a few moments. Well, at the end of this lecture. Yeah, it's not straightforward. You shouldn't rename the HTML file to .ts because, of course, that wouldn't work. Right. This is a simple exercise. So now we will be moving to a section where we combine TypeScript with JavaScript code. Why would we want to do that? Because we live in a JavaScript world. TypeScript comes from JavaScript, and it can use JavaScript code. It is capable of that. Why would it want to? Because there's a lot of JavaScript code out there that we want to be able to use. But that's JavaScript code. It does not contain type information. TypeScript, when we install it, has types for core JavaScript, so stuff like console and date. And it also has types for the DOM, like the document object and HTML input element. If I open this example, here's some client-side code, and I hover over document, and it's telling me that it's of type document. And if I hover over query selector, it tells me that it returns HTML paragraph element. It's clever enough to know that if I give it just P, it will return an HTML paragraph element. These types are already there in TypeScript when you first install it, but not TypeScript, the package, cannot come with types for absolutely everything. So there are a lot of packages on NPM. Node itself comes with a lot of built-in packages, and those are not typed by default in TypeScript. So how can we use them? I have an example here. This is in Node.js. I use the built-in OS package. You haven't probably seen it, but it gives us things like, tells us how much free memory we have in the computer, how much total memory we have there. So we can have a little tool here that gets those 2 numbers, subtracts them, and then tells us how much memory is used, how much memory is free, and how much memory is total in the computer. TypeScript is currently complaining. It's complaining up here that it cannot find module OS or its corresponding type declarations. TypeScript doesn't know Node. We have to tell TypeScript about Node. Node itself isn't written in TypeScript, so the maintainers of Node, they don't really care about TypeScript types for the Node built-in packages. Where do we get those types? There is a project called Definitely Typed, and it publishes a lot of packages on NPM that are prefixed with @types. One of them is @types/node. If I go to my terminal and do npm install save dev @types/node, then that goes quickly. And if I close this, I go back here, TypeScript isn't complaining. It now knows about OS, and it knows that OS has free mem, and that free mem returns a number. So now I have typing for all of the built-in Node packages, and it's really, really useful. And I can run this, and it will show me that I have 32 gigs of memory. Oh, nice. that I have 500 megs of memory free. I think that's just for Node. So Node thinks that 31.5 gigs of memory are used. Fair enough. I will show you how to do this with not built-in packages as well. I will use a package from NPM called seed_random. I have here a program that uses it. I haven't installed seed_random yet, intentionally. So npm install seed_random. Seed_random also doesn't come with types because seed_random is written in JavaScript and the maintainers don't really care about TypeScript. But somebody has contributed types seed_random. So npm install savedev types seed_random. That finished. And now in here, seed_random is known. Now, what is seed_random? Let me go to the page. The page tells me that it is a seeded random number generator. You know random number generators, math.random returns a random number. A seeded generator, you can give something called a seed to, and then with that seed, it will always generate random numbers in the same sequence. If you change the seed, it will be completely different random numbers, but the same every time you use the same seed. It is really useful for repeatability if you want some kind of randomness in your program, but you want to be able to repeat runs and have the same results. So here I use seed_random. I create a random number generator by calling seed_random and giving it a seed. Now, how do I know what seed I can give it? When I'm typing this, I can type this and it's telling me seed is a string or undefined. I don't have to give it a seed, but if I do, it's a string. So I type the string hi, because why not? And then RND is of type seed_random.prng, which stands for pseudo random number generator. That's what it is, of course. And then I can use RND to generate me random numbers. This program first shows 3 random numbers by seed_random, then it shows 3 random numbers by math_random. And the function show just shows 2 digits because otherwise it gets a bit messy. So I'll run this. Seed_random has 218874. Math_random has 38927. I'll copy this out. And so we'll remember this. I'll run it again. Seed_random gives me 218874. That's the same. Math_random gives me 537573. Different numbers. This is how we can use NPM packages and yet still have the type annotations that we want for nice statically typed programs. So we know here, for example, that RND returns a number. It is a function that returns a number. So very good. The types in the definitely typed project, they are usually contributed by users of packages. If a maintainer wants to type their package, they can include the types right there in the package, and then we can remove @types, because a lot of packages come with their own types out of the box. Let's look at how that works. I'll switch to a different scenario now. You might have a JavaScript project and you want to migrate it to TypeScript. What you don't do is just rewrite the whole thing from scratch in TypeScript, because that would take long and it would be, you couldn't test along the way. It would just be a bad idea. What you want to do, because TypeScript can interoperate with JavaScript, you want to migrate your project file by file. Usually we can try to do that by going up the dependency tree. Some modules depend on others, but some modules at the bottom of the tree, if we put the root at the top, those modules will not depend on anything else. So we can easily convert them to TypeScript. When we compile it, it becomes JavaScript again, and modules that use this use that JavaScript. That's fair enough. So these modules that don't depend on anything else, we can convert them to TypeScript easily. But sometimes we don't want to convert a module to TypeScript just yet, but we have other modules that we do want to convert, that we do want to use this module and get type information. I have an example here in the code. I have a JavaScript module, 3JS module.js. It just exports a function that takes two parameters and returns the sum of them. So this is the typical add function, right? This is a JavaScript module. We don't want to convert it to TypeScript just yet. We want, however, to use it. I have here 3B TypeScript using JS modules. We want to import add from that module, and we want to run add and give it the parameters. So I will run this. It's not complaining about anything. I will run this, and it returns 7, which is good, because that's 3 plus 4. And if I tried to run it with strings, it would complain. How does it know that I can't do strings? I didn't tell it. Actually, I did tell it in another file, a special file called 3js module.d.ts. It's the same name as the 3js module, but the extension is .d.ts. If I open it, it only gives us the function declaration. It only tells us that there's a function called add, and it takes an a, which is a number, b is a number, and returns a number. So we can have this, and we can go in there. If I remove this file, for example, by calling it 3js module2.d.ts, if I go back to the TypeScript code, it still can import 3js module, but it doesn't know about add. So add is taken to be a-any, b-any, and any. It does parse the JavaScript. It knows it has two parameters, but it doesn't know their types. It doesn't know what add returns. And if I try to call it with string, it will let me. I can prevent that by having the file d.ts, and then TypeScript knows that strings are not expected there. So we can add .d.ts files to any JavaScript file, and then we provide explicit typing. And that is very, very useful when we're migrating. Good. That was interoperability of TypeScript with JavaScript. Let us now look at two very interesting programming techniques called overloading and generics. We will get to them momentarily, but we have to start with more about how we type functions. We talked about functions. We annotate the parameters, we annotate the return type, and everything else. I've already had that on a previous slide. When we talk about a function, the parameter types and number of parameters and the output type, that's called a signature of that function. So a function signature can be used as a type. We can have, and I have that here, we can say R1, that's a variable, is going to be of type a function that doesn't take any parameters and returns a number. So here I'm declaring a variable R1. It will be no parameters and returns a number. We have a function like that in the math library. So into R1, I can assign math.random because that is a function that doesn't take parameters and returns a number. When we have types, we can give them names. So far, we have seen that with interfaces. Every interface has a name. But we can also create names by the keyword type. These are called name aliases. So number function is a type that actually is just an alias for a function that takes no parameters and returns a number. So I declare here a variable R2 that is a number function. And again, because math.random fits that signature, I can assign math.random to R2. And I can call R1 and R2 as functions because they are functions. So they return 2 random numbers. Fair enough. This will become useful in a few moments. I have one more. We can also have functions inside interfaces. We can say a fun interface has a property called fun, which is a function that takes no parameters and returns a number. And again, we can create an object that follows fun interface, and it has fun, and we put math.random in there. What we then can do is call fun, and r3.fun also gives us a random number. This is all type checked. How do I know? I could try to assign console.log into R1. Console.log does not return a number, so TypeScript complains, because I can't have console.log as a function that returns a number. I can't put console.log in r3.fun because console.log doesn't return a number. It doesn't fit the signature. So that's function types. What we have here is an example that we will use a lot in the coming slides, sorting. Let me go there. Let's say we have an interface person. Every person has an age and a height. And we want to sort people. And sometimes we want to sort them from shortest to tallest. And sometimes we want to sort them from youngest to oldest. So we make a function that takes an array of people and a comparing function so that it can compare two people by whatever way we want, and then it can sort them. This is exactly what JavaScript also does. So we actually just use the JavaScript built-in sort function to do the sorting. But I want you to see the typing of this sort people function. In JavaScript, it would just be a short line. Function sort people are compare. But we wouldn't know any typing. So in TypeScript, we could put it on a single line, but it would be a very long line. On my screen, it would very likely fit, but it doesn't fit on every screen. And this line is 96 characters long. It really is a very long line already. So we put it on 4 lines. We say that array is an array of person. Compare is a function that takes a person, another person, and returns a number after comparing them. Negative number if A is smaller, positive number if A is bigger, and so on. Then we can have 2 functions, compare by age, which takes 2 persons and returns the difference of their ages. We can have compare by height, which returns the difference of their heights. And this way, we can sort people by age or by height. If we have people, which is of type array of person, and we have here age 18 and height 180, we can add another one with age 20 and height of 170. Then we could sort these people. Here, I'm calling sort people, I'm giving it the array of people, and I want to compare by age, so I want to sort them by age. What is the type of sorted? When I hover over it, it tells me it's an array of person, because sort people returns an array of person. So this is an example where we use a function type like this so that we can say we expect compare to be a function, and it wants to take 2 persons and return a number. We will come back to sorting in a few moments. Sometimes we want to have multiple type signatures. Here I have sort array that doesn't need comparison, because if we give it just numbers, we know how to sort numbers. We don't need an extra function. So if we give sort array a number array, we want to return a number array. If we give sort array a string array, then we want it to return a string array. We don't want to lose that type information. This is called overloading. This is a single function sort array that has 2 different signatures. So how do we do that in TypeScript? In JavaScript, we don't need that because we don't have any typing. But in TypeScript, we define the function. I'll get to the definition in a moment. And we declare the signatures that it supports. only the declarations are available. This signature is not available for use. This is just the internal implementation signature. So how does this sort array work? We have an array which is either a string number or a string array or a number array. If the first item there is a number, then we sort it as a number array. Otherwise, we just tell JavaScript to sort it, and JavaScript by default sorts as strings. So this function can take a sort array, can take either string array or a number array, and it will sort it correctly. It will not sort numbers as if they were strings. Now, how does the typing work? If I have two variables, array1 and array2, array1 is a number array, array2 is a string array. If I sort array1, sorted, the output is a number array. But if I sort array2, the output is a string array. You can see that TypeScript has inferred that sorted has to be a string array when I've done that. So when I'm doing it this way with a string array, I'm using this declaration of the function. And if I give it a different array, I'm using this declaration of the function. And if I try to give it an array of numbers and strings, then it tells no overload matches this call, because no sort that I have declared can take numbers and strings at the same time. That is called overloading. Right. You will see overloading a whole lot. In JavaScript, that is a common practice to be able to accept different types of input and then return different outputs based on that. So the implementation has to use a combined type. So you've seen that the array is either a string array or a number array. It returns, in this case, any. We just turn off typing there because we know it's going to be either number or string. And the implementation has to check the type at runtime. It has to find what kind of parameter it's actually dealing with on its own. So moving on from this, what if we wanted to have that generic sort? A sort that takes any kind of object and a function that can compare those two objects and returns a number, and then the sort returns those objects, right? So I can declare it like that. I can have a function like that with no overloading at all. It's all nice. And I can declare an interface person. I can have an array of people. It doesn't matter that we only have one person. I can have comparison by age, which takes two people and compares their age. And then I want to call sort array. Oops, TypeScript complains. Compare by age wants person, but in here, we know that it's an object. We don't know that that's a person. So when we give those, so array.sort takes items from the array and gives it to compare. So if we know that array just has objects, we don't know that they are persons. Compare by age requires a person. TypeScript cannot guess that every item there will be a person. So we can't use compare by age. We have to turn off typing. I use any here to turn off typing, and that problem goes away. But I have lost any type checking inside compare by age. That's not a good thing. And now let's have a look at what the outcome is. Sort array returns an array of objects. So outcome is of type array of objects. So if I try to get the age of the first person in the array, I can't, because objects don't have age, persons have age, but that object is not guaranteed to be a person. So we have a problem. The comparator didn't fit and the output doesn't fit. This kind of function, it looks very generic, but it doesn't work in the type system. We have to try and do it differently. I will switch now to a different example, a simpler function that has the same problem, and that's a pick function. This function takes an array of anything and just picks a random item from that array and returns that. So if we give pick an array of numbers, we expect to get a number. And if we give pick an array of strings, we expect to get a string. And if I give it an array of numbers, I hover over outcome, it's telling me outcome is any. We lost type information here. We don't know that outcome is a number because we are saying it's any and we return any. What we really would like to have is an overload of this function for every possible type. So we could overload the function for numbers. And then if we give it a number here, an array of numbers, outcome will be a number. But we couldn't give it an array of strings because we don't have that overload. So let's add that overload. We give it an array of strings and we return a string. And then outcome becomes string. So that works. But we would have to overload it for droid and for contact and for person and for every other type that we define. It is not right. We can't overload for all possible types. And that's where the idea of generics comes in. This function, pick or sort, they want to be generic to any type you give it. And we have a mechanism for that. On the slide here, I have a function pick that takes an array of t, whatever that is, and returns just one t. And how do we know that t is not meant to be a type, but a variable, but a type parameter? We give it here in the angly brackets. So when I move to that, I have that pick in here, and it says for any type t, this function takes an array of that type and returns an item of that type. So if I have an array of numbers and another one of strings, if I take array 1 and give it to pick, the outcome will be a number. And if I take array 2 and give it to pick, the outcome will be a string. Now Typescript can take the value from here, the type number, sees that it fits its t array, so t must be number, so this must be number, and with array 1, it will return a number. And it works with arrays like this as well. And if I put 1 in here, then the type of this array is, it has strings or numbers. So y is going to be string or a number. Typescript knows that. It's brilliant. This is called generic, and you will see that a whole lot once you start using Typescript. A lot of functions are defined as generics, and you will see another example in a moment. With this, we can do a generic sort. We can have a sort function that takes an array of numbers, returns an array of numbers, a sort function that takes an array of strings, returns an array of strings, and another overload, a sort function with a parameter t that takes an array of t and a function that takes one t and another t and returns a number. And that function returns an array of t. So down here, I have an interface person. I have the array of people. I have compare by age with full typing. I know that A and B are person. And I sort the array of people. Sort array now becomes parameterized to person, and outcome is an array of person. Because this type, this t, gets assigned to person because we have given it an array of person. So then in the outcome, we can get the age because we still know that it's an array of person. This is very powerful and possibly takes some getting used to. So play with this code and tweak things and read the handbook. On the previous slides and on GitHub, we have a link to the TypeScript handbook. That is the reference to the language, and it is very good read. So one more thing. When we deal with programs, some data is out of our control. We can, in TypeScript, type everything that we create inside the program and that we consume inside the program. But some data is out of our control, especially when we deal with network or storage. We can have data that isn't guaranteed to be of some type. When we have data incoming from the network, we need to check it. We need to check that it conforms to our expectations. Otherwise, we might have risky, misbehaving programs. But when we have outgoing data, we can still have the typing. Let me show you that. I have an example here with Express. So I have an Express server. I haven't installed Express, so I'll do that. npm install Express so it can run. And I will also need to install Typescript because Express doesn't come with its own types. So install save dev types Express. And when I do that, now Express is typed. I also import pic from the previous slides. We might have a server that just has one route that returns a person. And we will have a function called sendPerson that handles that route. And we start the server on port 8080 as usual, fair enough. What does the code look like? We have an interface person like before. I have added a name here. I have two people, Jack and Rich. Rich is slightly older and much taller. And the function sendPerson, to be able to be, for us to give it to app.get, it has to have a request of type express.request and response of type express.response. But with a type parameter, we can say that the response will respond with a person, right? So what we have here is we use the pic and we give it people, it picks a random person and it gives it to rest.json. Rest.json expects a person here because we have said that it should. I will run this. That's going to be ts node source server 1 express server. And I will go there from here, localhost 8080. But of course, the root is at /person. And I got Rich. Rich, you win. And if I reload, I still get Rich. And if I reload, I now get Jack because we return a random person. So this is how we can type the outgoing data. And if by some mistake I try to output something wrong, like a new date, then it would tell me that argument of type date is not assignable to parameter of type person. We can make the computer check our expectation. And here we expect that the response will return a person. And that is really good for making solid programs. Right, back to my slides. Oh, this brings me to a project idea. If any one of you is struggling for project ideas and you feel like it, you could take it on to try and extend the TypeScript language so it could generate from type definitions like this, runtime checkers for data. So when we get a person from the interface, from the network, it could check, is there a name, is there an age, is there a height, are they of type string number? If so, we have a person, we're happy. TypeScript currently doesn't have that. There are roundabout ways of doing this, but it really wants to be a function or a feature of the language. And we have had previously final year projects where somebody extended a popular language. The last bit today is about environments again. I have added one more line to the TS config. So if you start a TS project, add ES module interop true in your TS config, and it will make the software like mine run. Beside that, when you're working in Node programs, instead of Node, you should use TS Node. Instead of nodaemon to automatically compile and reload your code, you can use TS Node dev, and those are all on NPM, and that's it. And you can set up your editor, VS Code or Atom to automatically run TypeScript scripts in Node, and that's really nice. So that's easy. That I already covered that last week. How about browser? Last week, I told you you have to compile the TypeScript into JavaScript. The HTML has to point at that JavaScript, and that's just terrible. I will show you a tool called Parcel. This tool is, it has version 2 in development. There are other tools like that. It's just one example of these tools. Parcel is particularly easy to use. It may not be as powerful as others, but it's easy to set up. What you can do is npm install Parcel. You have to do @next, so we have the version 2. And then if you have a HTML file, and I have that here, HTML file that points at a TypeScript file as a script, and then you have a TypeScript file that works in that HTML file that takes the first paragraph and replaces it with hello world. Initially, there's nothing here there. You know from last week that this doesn't work out of the box. The browser will not understand TypeScript, but you can tell Parcel, I will close this bit now, and I will tell Parcel. So firstly, npm install save dev Parcel @next. And when that's there, I can then let Parcel serve my file to me on a development server. So once this finishes, because this takes a bit of time the first time you do it, you will just run a line like this, and then Parcel will give you the compiled output of the file. These kinds of scripts really want to be in package.json. So I'll go to package.json and show you. I have added two scripts, start Parcel example and build Parcel example. Start Parcel example uses Parcel serve, and it gives it the one hello world HTML file. And build Parcel example does the same thing, but it outputs the compiled stuff so you can put it in your web hosting. When it finishes, I can then show it to you running. I have added --no cache because Parcel v2 is in development and sometimes the cache gets in the way. So it's sometimes better not to use it. So npm run start Parcel example. It runs Parcel serve, it compiles everything, and it tells me that it runs on localhost 1234. So if I go there, the file name is one hello world.html, and then I have it, and it works. And how do I check that it really works, that it isn't just some compiled stuff from before? I go in the TypeScript file, which is in here, and I change hello world to hello y'all. I save this, and already it changed here. I didn't have to do anything. Parcel tells your browser to reload it automatically, and it recompiled and reloaded for you right there. So I changed this by just removing it, save, and in a few moments it's there. And this is TypeScript code. I can say HTML element, HTML paragraph element or null. So yes, it can be null. So now I have added the type annotation, and I changed this, and it still works nicely because this is TypeScript. It's fully type checked, and Parcel is compiling it for me and running it. And Atom is telling me about any problems. With Parcel and other build systems like this, we can easily use TypeScript in HTML. What does Parcel do? It compiles the TypeScript, obviously. That's what we used it for. But it also puts all the TypeScript files in a single JavaScript file, so the browser has an easier time loading it. It minimizes everything. We can have a look if I run this with build Parcel example. We will see the output of it. In HTML dist, I have one hello world HTML, and it links to one hello world with a hash.js. And if I go to that file, it's very short, but it's very, very dense. That's so that the source code is shorter, and again, the browser has less work downloading it and compiling it. To conclude today, static typing is a powerful tool that finds some type errors. It will never find all of them, but it will find some of them, and it finds them while you're typing. You don't have to run your program to find the errors. It finds them for you as you are typing, which is brilliant. But there is a cost to it. There is more keyboard typing. We have to put the type annotations in. There's more thinking involved. Actually, that's not a cost. That's a positive thing. And there's the build system. We have to deal with having to rebuild stuff as we save. We can't just save and reload in the browser and that's it. But there are tools that help us do that. We learned today 2 new programming techniques: overloading, where a function can have multiple type signatures, and generics, where we can have types with type parameters. And then, for example, functions can react to the type of the parameter. But we still need to check incoming data. We are here doing a lot of web programming. We deal with a lot of incoming data from the network, from storage, and we need to check it. And that's where tools like Typescript do not give us any help, because they can't. That data is a runtime thing. It doesn't fit in static type checking. The costs of TypeScript and systems like that are big. The benefits of that are even bigger, especially on big projects. So as you do bigger and bigger projects, you will very likely start running into type errors, avoidable if you are more careful, but we are just human. So static typing helps us find a lot of those errors right there as we type. So do that example where you take our erroneous programs in JavaScript, turn them into TypeScript, and see how that helps you fix and find the problem. And try TypeScript in your projects. There's a playground linked from Moodle. There's a handbook linked from Moodle. Have fun with that. Any questions before I go to my next class that started 4 minutes ago?
Yeah, I've got one quick question.
Yes, please.
If you go back to example 13.
Yes, 13 pick.
The pick, yeah.
Yep.
And on line 4, if you
Yep.
change the second any to number or string, would that work?
Number or string. Cool. It works here because this any turns off type checking inside here. Now, what is the type of outcome? We gave it an array of string, and no, it says string or number.
Is it okay to do it then? Because that kind of eliminates the need of the overload.
But we gave it array 1, and it's an array of numbers. If we want to deal with outcome as a number, we would have to typecast it again. We would have to say something like outcome number, but of course it doesn't allow us to, because it might be a string, as number. But that's a lot of typing. We are losing type information through this any and through this, and we would have to reintroduce it here and hope that we didn't make any mistakes. Overloading is an absolutely normal way of doing it. It's not expensive. It's not difficult once you get used to it. And it really allows our programs to be shorter, because we have fewer definitions than uses. So if we had to do, oh, I already lost that. But if we had to do outcome is pick as number, then of course we change this to that and forget that it's not a number. So it would pick a string for us, but TypeScript would think that we have a number here. And we would get into terrible problems at runtime. This would be possibly a runtime problem. But JavaScript is happy to deal with strings and numbers together. So it would be a very subtle and nasty problem. We want to avoid telling TypeScript, changing TypeScript's mind as much as we can. We really want TypeScript to do the work for us, and the overloads are the mechanism to do it. It's
Okay.
not like we are doing something really complicated extra. This is absolutely a normal pattern of working in JavaScript and TypeScript. Does it make sense, Arek?
Yeah, it's cool. Thanks for that.
Thank you. Yeah, that was a good one. Thank you all very much. I hope you like TypeScript. It is putting a lot of thinking and work on you, but the costs are worth it. And you will very likely be expected to know static typed languages when you go to work on big projects in the industry.